Hello, everyone, and welcome to the February 2026 LINCC Talk. My name is Olivia Lynn, and our co-host is Colin Orion Chandler. We're both members of Link Frameworks. I'm a software developer at the McWilliams Center at Carnegie Mellon, and Colin is a project scientist in the Dirac Institute at the University of Washington. Link Tech Talks include presentations and demonstrations that showcase work done by the broader Rubin software and archives community with the goal of further enabling LSST science. Unlike traditional talks you might hear at a conference, here we highlight the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss the efforts of interest and in the analyses of LSST data. Link Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific or 1 p.m. Eastern. Our speaker today is Argyro Sasli, a postdoctoral researcher in astrophysics at the University of Minnesota, working on machine learning for time domain and multi-messenger astronomy, including applications to gamma ray bursts, gravitational waves, and transient electromagnetic counterparts. She is a co-leader of the AppleCiDEr project and focuses on anomaly detection and automated multi-wavelength and multi-messenger follow-up. For the talk, please ask questions in Zoom or in the Link Tech Talks channel of the Discovery Alliance Slack. On Zoom, you can type questions into chat or raise your hand. As a friendly reminder, these talks are being recorded and they will be posted on our YouTube channel afterwards. And with that, Argyro, please take it away.
Thank you very much for the introduction, and thank you for inviting us to present the AppleCiDEr. So today I'm gonna talk about the AppleCiDEr project. We are a huge team, so that's why I'm saying on behalf of the AppleCiDEr team. And what I will present is more on towards a scalable multimodal transient classification for Rubin-Era alert streams. So what is our motivation for this? So with ZTF, we already have many alerts per night, like 10 to the 6th. And with Rubin, we are gonna have even more. So a huge amount of alerts. And what we want to do is to trigger follow-up for the cases that we are really interesting. But of course, depending who you ask, the interesting source could be something else. For example, rare events or some subtypes of supernovae type 1, let's say. So the whole idea is that we have the alert stream, then we can have some contextual enrichment through the different brokers, and then we can have a unified multimodal AI inference with which we can perform classification, anomaly detection, and uncertainty quantification. Then the outputs will be in a way that we have a unified decision representation, and then we can trigger automated follow-up. And of course, we always need a human in the loop to review and see how well we perform and whether this is really interesting and so on. And what we want at the end is to be able to, as we have new observation, to better train our network and perform more accurate classification and anomaly detection, of course. The question is why follow-up is important. Follow-up is really expensive, so we cannot follow up everything that exists out there for every alert that we get. And follow-up is important because let's see, for example, here the cartoon, and let's consider that we have a binary neutron star merger. Then we can extract information for this event through different phases, and each emission component corresponds to distinct physical ejecta channels, motivated, coordinated multimodal detection and follow-up pipelines. What I mean with this is that let's focus on this phase. So we can extract information with gravitational waves and with gamma rays burst with GRBs. But if we want to focus more on this, then we can extract information through the GRB afterglow. But if we focus more on this phase, then we can have, for example, images, metadata, spectra, and spectra through all the phase, of course. And here we can get more information about the kilonova component. So as you can see, there are different stages and different data products that can help us to understand the event. And in case of an anomaly detection, these different phases can contribute to learn more about the environment, if it is an anomaly based on the environment, or if it is an anomalous event just based on of the physical mechanism of this event. So follow-up and multi-wavelength follow-up is really important. However, in order to have a multi-wavelength follow-up, which is really expensive, we need to be very confident about our trigger of opportunity. And in order to do this, we have to overcome some challenges. We have two different types of challenges. One comes from the data itself, and the other one comes from the machine learning perspective. So we have data that is heterogeneous. We have different modalities, like we have images, we have metadata, time series, for example, photometry. We have spectra, GRBs, gravitational waves, and so on. Also, we can have missing channels, which means, let's say that we have from the Rubin alert, we have the images, some metadata, and the photometry, but we lack from spectra. And what happens when we have also spectra? Can we be able to evaluate and make a decision when we miss some information? And we have latency constraints. Of course, we want to react as soon as we can. And this means that we need something really fast, but also to be able in a position that we can evaluate the data with some minimum amount of observations. So from the machine learning perspective, we have to do this with early classification, which means incomplete data. For example, let's say that we have 10 days, just 10 days of photometry and images. How well can we do? Of course, if we had more, like 50 days, we will have a better classification. And also, when we talk about machine learning, this means that we have some data with which we have trained our network. So what happens if, for some reason, our data is not full representative, and it's not going to be full representative? So we want to be able to also classify outliers in our data or trigger them as an anomaly detection. And since the last years becomes more and more urgent, we need classification with some uncertainty quantification, so we can say, yes, this has a probability of 0.8 to be, let's say, a supernovae type 1a, but with this uncertainty in our classification. So for the first paper that we have, that we had the AppleCiDEr, here is the team, but now we are even bigger. We have more and more people. Michael Coughlin is the PI. Here is me, postdoc, Felipe, who is the graduate student in our department, Alexandra, who was postbac in our department, Benny, an undergrad, and Mauhe, an undergrad, back then when we starting building AppleCiDEr. And So what is AppleCiDEr? AppleCiDEr is a multimodal network in order to classify early data, photometry, images and metadata and spectrum. And here is also the GitHub that we have. And in this first paper, we just averaged the logic. So it was a simple fusion model that averages the classification of the logics of the three different networks. So how it works, we have these three different networks, each one for their modality specifically, and then we just average. So let's go to the first model, which is the SpectroNet. SpectroNet is a model that is trained with spectrum from different classes, and is a CNN, multi-scale CNN architecture. So we have 5 spectra blocks. Each spectra block has a large scale, medium scale, and small scale convolutional autoencoder, 1D. And then the three convolutional autoencoders are concatenate, and then we downsample and then pass to the next spectral block, and at the end we have an adaptive max pool. Then a fully connected layer follows another fully connected layer, and then we have the classification output. So this is just for spectrum. Then the second model is the Astromin, which is a work led by Benny. Benny is an undergrad in our department. And what we do here is to have some towers, and each tower has a specific some group of specific characteristics from the metadata that we have. And then we have also a convex tiny backbone, which has two different heads. So the images come through this first architecture, and then we have a main head for the classification and bending space, and another head for the position in the sky encoding. And then we fuse the metadata from the towers, and then also the embeddings from the convex. And as soon as we fuse the outputs and the image embeddings, then we pass them into the mixture of experts. And this mixture of experts accounts for three different experts, which go through the 3 MLP multi-layer perceptron networks. And then based on the weighted average of the selected experts, we extract the classification outputs. So for that model that we had back then, the performance is very similar to what now have with the BTS model, but we are working also on some upgrades of this model, and so the architecture will change a little bit. And yes, the other model is the tempo model, which is for the photometry. This is something that led by Felipe. So we have tempo, and we have a vector of different inputs, which takes into account the flux for the light curve, the errors of the light curve, the difference in the time, like this is where the first time that we observe, and this is the nth time that we observe this. And then follows a linear projection, and this goes to a time encoding, and we have the transformer encoder, and then as output we have the the different embeddings, and then we can perform the classification. So the first results for AppleCiDEr are these. So as you can see, let's say that we don't use any information for the spectra that we have. In that case, you see that we cannot actually identify any TD, which is tidal disruption events, and we have a huge confusion between the supernovae type 1 and supernovae type 2. However, if we add the information for the spectra, so let's say that we have spectra in our data, and then we don't have only 2 networks but 3 networks instead, we are able to classify without any huge confusion the supernova type 1 and supernova type 2. But still, we don't have a great performance on TDs. Why is that? This is just because we have TDs are really rare events, and we don't have enough data, which means we cannot perform very well. And this comes to the challenge that I mentioned before. What happens if we want to trigger unexpected or outliers or rare events? Then just having a network for classification is not enough. So now I will start talking about more on the incubator program. So here is the team for hierarchifying the AppleCiDEr that I presented in the previous slides. And I'm really grateful to the software engineering team because it was really, really good experience. They help us a lot to build AppleCiDEr and make it more a clean repo, ready for production, and frame it like as a package, because before that it was not in a good shape. But also they help us to learn about hierarchies, which is really important for Rubin, and I think it was a great experience. So what were our technical challenges? Similar to what I mentioned before. So, but also our goal was to deliver a package ready to use for production, and we need to overcome data and machine learning challenges to build our infrastructure, packaging, reproducibility, and etc. But also we had to, in order to be able to do this, we had to overcome some data challenges and also machine learning challenges. And so even if before with AppleCiDEr we trained the networks and we were able to somehow overcome some issues, when it comes to have a package, then you need something more unified and more ready for production. So yes, we had to overcome these data challenges from that perspective, but also we had some machine learning problems, challenges to overcome, which is we actually the engineering team had to build some new functions that were needed for our models, and these functions weren't available in hierarchs before. And also we had to make possible the onixification, which is also very critical for production. And some models, some architectures, the way that they were before, weren't really able to onexify it. But with some changes, I think after this incubator program, we were able to onexify every architecture that we had. So what we achieved through this incubator program was to actually be able to build and overcome the data challenges. So we had to build a unified infrastructure in order to have all the different heterogeneous data and also be able to pre-process the data. So here is an example you can call AppleCiDEr, that pre-processing utils, that pre-processing multimodal, and then you can import the config, the build all, pre-process, and compute futures, etc. So now someone can do this and just add from the config the different uh, uh, the where the data lives, but also the CSV files for spectra, for example, and also images, photometry, etc. And the next step was to build a multimodal dataset for machine learning training and evaluation. So yes, we have the infrastructure to pass all the data that we have into a unified framework, but we need also a unified data loader. So now in AppleCiDEr there is the multimodal dataset where you have first, of course, to build the manifest, and then you are able to use this in order to pass it through the AppleCiDEr network and then be able to train AppleCiDEr. And next, also, as I said, we had to use hierarchs for our model. So now you can just import hierarchs, and then by choosing a specific config file, for example, for the astromin model, you can prepare the training, and then you can just, with aids.train, you can just start training the model. Of course, in the config file, you can change the different features of the network, so you can do different trainings. And you can do exactly the same for the spectra model, and also for the tempo, which is for the photometry. And as I said before, we needed to also have a onyxification, a successful onyxification, and this can come with just H.2 onyx. So in that way, you can extract the onyxified version of, let's say, the astromin model, and then you can again perform inference based on the onyxified representation of the model. Or if you have trained, you can just say h.infer and start the evaluation of the dataset that you want to classify. And lastly, as I said before, AppleCiDEr was not in a place that we can have it as a package, but now, with all the help from the engineering team, we have a packaging. We have many examples there, and it's ready for deployment. So if anyone wants to play with this, with AppleCiDEr, and train their models, they are able to do it. And what are some next steps? So as I said before, we have a way bigger picture for AppleCiDEr. So this was just the beginning. we need a way better way to fuse the modalities and the different networks for just averaging the logics, but also we want to be able to just instead of having a classification to have an uncertainty quantification with our classification, and this whole thing is Felipe is leading this, and we have many undergrad students who are helping with that. Unfortunately, I don't have the photos from these two students, and we are getting also bigger and bigger because more people from our department want to participate in this. Also, another urgent thing that we really want within AppleCiDEr is to perform anomaly detection, and also we have two students that help with that. And the final step is to be able to run online in production. So we have Antoine and Suzanne who are working on this to integrate AppleCiDEr into Boom and Bamalum in order to be able to have all this into production. So regarding the fusion model, the idea is that instead of just averaging, have another network that performs all together the training, and based on the training and during the training we are fusing all these networks. So this is what Felipe and some other students are working on. And I don't have here the final results, but it is even better than the results that I had for the first AppleCiDEr. And as soon as we finalize the model, then we again gonna hierarchify the model. So it's gonna be in the AppleCiDEr repo, and anyone can use all here, all the previous functions for querying data, build and pre-process the data, and have a multimodal data set. And then instead of, let's say, just training the astronomy, they can train the more elegant, let's say, fused AppleCiDEr. And then another step that we want to do is to, as I said before, to perform anomaly detection. So since we have already AppleCiDEr, which performs classification, the idea is to follow a representation-based anomaly detection, which means we will extract the bendings from AppleCiDEr, and then based on this, we have different matrices that we can compute and extract an anomaly score. For example, I have here just two examples. One is the KNN, and the other one is the energy score. So as you can see, depending on the metric that you use, you get different anomalies. So we have more methods to do this. So the idea is at the end, we ensample all those methods and have a unified score for the anomaly detection, so that we can be sure about whether we want to trigger an anomaly or not, whether this is really an anomaly or not. So this is a cartoonist, let's say, representation of our final goal. So we want to have the photometry data, images, metadata, and also spectrum. This will go through the AppleCiDEr, and then AppleCiDEr will perform classification with some probabilities and uncertainties, but also we will trigger also an anomaly score. And if this anomaly score is low, okay, we don't care. But if this anomaly score is high, then we want to trigger multi-wavelength follow-up and also light curve parameter estimation. Yeah, thank you.
Thank you, Argyro. We do have time for some questions, and as a reminder, feel free to ask questions by raising your hand here on Zoom, asking in the Zoom chat, or posting on the Link Tech Talks channel on the Discovery Alliance Slack. Jeremy.
I can start. Thank you. This is a really, really interesting presentation. So as you discover anomalies, as you start processing the data, I imagine there'll be a need for new models to classify new parts of the space. Any idea how many models eventually? You presented the 3 that you've been training plus the fusion model. Is the thought you're mostly going to try to stay around those 3 or expand out?
Yeah, so here, for example, I have just 2 different metrics, but also we are investigating also, for example, normalizing flows, which is also another network to perform anomaly detection. But we are trying to minimize the number of networks that we want to use. So here is more kind of building also a good data set and a representative data set to make sure that we don't need anything more. So, for example, in order to be able to make this decision is to, as I said, to have a representative data set. So what we are working on now is to have a data set that this is our main data set. We are very sure about what we have here from the ZTF alert streams. And also we have some rare events like tidal disruption events or, for example, fast blue the F bots, or even some unknowns that we don't really know what it is. So the first step is to be able to perfectly classify the events that we already know what these events are. Then the next step is to be able for the rare events that we have enough data set, but not enough to be able to train the network, to be able to trigger them as anomalies. And then the last step, where it's going to be our decision whether we need more networks or not, is to evaluate the data set of the unknowns that we have and see whether whether these events go into assign the rare events or some classes that we know but could be outliers. So it could be a supernovae type 1a, but for whatever reason it's a statistical outlier, or if it's really something new. So that's why it is really important to have all the information that we can get in order to be able and make sure that we have a real anomalous event or not, and whether we need to have another network or not for this.
Thanks.
Thank you.
Kostya, go ahead.
Sorry, I was muted. Very nice talk, thank you. Similar question, actually. I'm interested in active anomaly detection. I'm generally in active human in the loop things. So do you plan anything like that here? Do you plan like personalized classifiers, anomaly detectors? And how do you see it would work in production?
Yeah, so yes, we have many different ideas of how we can do that, but in order to have a final decision, we need to evaluate the data set that I mentioned before. But yes, if I go back, like here, so the idea is that let's say that we have AppleCiDEr, which will run with the Boom Bambalum brokers, alert brokers, and then we can perform classification, uncertain quantification, and anomaly detection. So in the very beginning, we are gonna trigger some anomalies, right? So the thing is, as soon as we have it in a silent production, not online, offline, we will see whether these anomalies are really anomalies or not. And then comes the question about whether we really want to somehow, for example, reinforcement learning, to have also the whole network, the whole pipeline, to understand whether this is an anomaly, really a really anomalous event or not, and update the whole model in order to be able to classify better and perform anomaly detection.
But it is like a single model. So when you say we, you mean like your team. And I'm like asking about personalized experience. So I'm like a user of Boom Broker, right? And I would like to fit anomaly detector or classifier for myself. Do you think it's like a useful idea, or do you think it's like too expensive to retrain the model for everyone?
I think everyone is welcome. Yes, when I say we, I don't mean we us specifically, but everyone is welcome to contribute and try the models. The models are outside, but also even help the whole team, AppleCiDEr team, Boom Bambalum team, to be able to use all this and perform anomaly detection. So, for example, I think will be very easy for you if, for example, you have an anomaly detection for images, to integrate this into Boom Bambamul and train your own network for the anomaly detection, or even another way is to use, for example, the outputs, or if you are more interesting, you can even use let me go here, the embeddings of the AppleCiDEr, and you can even do more stuff if you want.
Thank you.
I was just wondering, between those three individual networks you work with, do you find any of them perform particularly differently or better than the others? And does this differ across different types of objects beyond like the cases like TDEs, or there's just limited data?
Yes, great question. So I think the easiest one was the spectrum because it has the more information compared to others, and actually the performance was there was like okay, now we have 0.95, let's say, accuracy, and now we have a 0.93, so it was really different. Yes, because spectra are really, really useful. And I think the images were really, really, really challenging based on the different classes that you want to train. So I think the task of having just supernova type 1 and supernova type 2, AGN, CVs, blah, 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 for the images was very challenging compared to what BTS bot does, for example. And so that's why we wanted to work more on the astromean model in order to be able to have some better classification. And for the tempo, which is here should be third, sorry, it's one, but should be number 3. For the tempo, the most challenging part is that we wanted to have only 10 days, so which means only 10 measurements to perform the the classification, which is really, really challenging. So that's why Felipe did his best in order to have a very good model. I think, yes, this was the best model from whatever we have tried, because every other model can perform better and comparable to this model if we have 50 days or 50 observations or 100 observations. So yeah, so the days were the most challenging part, and that's why we came with this architecture.
Thank you.
You're welcome.
Last call for questions. All right. Well, thank you again for a wonderful talk. And thanks to everyone for attending the LINCC Talk series today. Our next talk is scheduled for March 12th. Stay tuned for an announcement. In the interim, please join the LSST-DA LINCC Talk Slack channel and the link at list.lsst.org mailing list for more information and future announcements. There is more information, including links to the Rubin Community Forum and a calendar at our LSST Discovery Alliance website. LINCC Frameworks is also holding office hours every Thursday at 10 a.m. Pacific or 1 p.m. Eastern, except when it conflicts with this Tech Talk series. If you have an idea for a Tech Talk, we'd love to hear from you. Feel free to reach out to us via the LSSTDA Slack or email listed at the Tech Talk website. And with the speaker's permission, today's Tech Talk will be available on our YouTube channel within the next few days. Have a great rest of your day or night, and thank you.
Thank you.
Mhm.